Hello. So we'll start in 2-3 minutes. Am I audible? All right. So let us start. So welcome everyone. This is week 5 discussion hour or problem solving session for the course strategy and introduction to game theory. I am one of the TA of this course. My name is Shubham Keshri and I'm a PhD student in the Department of Management Sciences, IIT Kanpur. Uh, yeah, so we will begin this lecture. So the format of this lecture is we will discuss problems, and through those problems we will see the concepts behind those problems. And if you have doubt, please unmute yourself and then speak, because you will not be able to chat in this. The option of chat will not be available at your end. All right. So the first problem which I have taken here is the discussion on what we were doing in the last class. So in the last class, we were talking about non-credible threats. Right. So for non-credible threats, we discussed that what a non-credible threat is, and we had some confusion. Therefore, I have taken this game, Battle of Sexes, which you are familiar, and this payoffs may be different from what it was discussed in the class, but the idea behind this game is same. So in this game, Battle of Sexes, there are two players, a girl and a boy, and both have two strategies or actions. Either they want to go for a cricket match or they want to go for a movie. So the girl can either choose cricket or movie. Similarly, the boy can either choose cricket or movie. Alright. Now, first we will solve this game using assuming that it is a simultaneous move game, and then we will solve this game thinking that it is a sequential game or extensive form game. All right. So when we are thinking this as a simultaneous move game, what we'll do, we will find the Nash equilibrium by finding the best response of each of the players, and whenever the best response intersect, at that point we will say that the Nash equilibrium will occur. All right. So for the action, when the boy plays cricket, the best response of the girl will be cricket. You see, cricket. Why? Because girl is getting 1, a utility of 1 instead of 0. Similarly, when the boy is playing movie, the girl's best response is to go for a movie. Okay? Because she is getting a utility of 2 instead of 0. Similarly, when the girl plays cricket, the best response of the boy is to play cricket. So I'll just change the color. And when the girl plays movie, the best response of the boy is to play movie. Why? Because he is getting a utility of 1 in place of 0. So if you see, there are two Nash equilibriums for this game. First is cricket and the other is movie. Right? These are the Nash equilibriums for this game. We have two of them, two Nash equilibriums. All right. And what are these Nash equilibriums? These Nash equilibrium are at which the best responses of both the players are intersecting. And one thing you should always keep in mind is that finding the best responses and the intersection of the best responses, this idea of finding the best responses and getting the intersection of best responses is crucial for this whole uh, course as a whole. All right. So in today's lecture also we'll see, when we talk about Bayesian Nash equilibrium, this idea of intersection of best responses will play a part. All right. So this is how we can find out the Nash equilibrium of this simultaneous move. What happens if this is a sequential game? All right. When we have a sequential game, then we'll have to decide which players play first. So suppose the girl player is playing first. When the girl player is playing first, so I'll write G. The girl player has two strategies to do. What are the strategies of girl player? The first, she can either go for cricket or she can go for a movie. Correct? And at the second node, the boy player will play. At the second node, boy player also has two strategies: cricket, movie, cricket, movie. All right. So we are saying that the girl player is the first player who is playing, and then the boys follows. All right. You can design this other way also. The boy player is playing first, and then the girl player is playing. Over here, I have designed the game such that the girl is playing first, and then the boy is playing. All right. So depending upon which node or which action the girl is playing, the boy will play accordingly. Now you see, we will write the utility at this terminal nodes or the leaf node. If you remember, in the last class, we talked about what are root nodes, non-terminal nodes, terminal nodes, and so on. So these nodes which are at the periphery are known as terminal nodes or the leaf nodes. All right, and this is a game tree. So what is this? This is a game tree. Now we'll write the utility. You see, the first girl is playing cricket, boy is playing cricket. So the utility is 1, 2. All right. When the girl is playing cricket and the boy is playing movie, so girl is playing cricket and the boy is playing movie, the utility is 0, 0. Similarly, when girl is playing movie and boy is playing cricket, so girl is playing movie and boy is playing cricket, the utility is 0, 0. And when girl is playing movie and boy is playing movie, the utility is 2, 1. Remember, the first player is the girl and the second player is the boy. So those utilities are written in such a way. All right. Now we will see what is the so using backward induction we'll find the Nash equilibrium of this game, or subgame perfect Nash equilibrium of this game. All right. So we will we'll perform the task of backward induction. So at this subgame where the boy is playing cricket or a movie, you see the boy will get a utility of 1 if he plays movie. All right. Now, so the boy will play movie. Therefore, this subgame will become as this subgame will be solved as 2, 1. All right. Similarly, on the other end, when boy is playing cricket, he is getting a utility of 2. Sorry, he is getting a utility of 2. All right. When boy is playing cricket, he is getting a utility of 2 instead of 0. Therefore, he will play cricket. Therefore, for this subgame, the utility using backward induction will come out to be 1, 1, 2. All right, 1, 2. I'll just erase this and rewrite it. So it is coming out to be 1, 2. Now you see what the girl will do. The girl will see what is the highest utility she is getting. So when she is playing cricket, she is getting a utility of 1. When she is playing movie, she is getting a utility of 2. Therefore, she will play movie, and this will be the subgame perfect Nash equilibrium of this game. So this will be the utility, and the subgame perfect Nash equilibrium is movie, movie is the subgame perfect Nash equilibrium. So you see, for this sequential move game, when one player is playing and then the other follows, you have only one subgame perfect Nash equilibrium. And an interesting thing to note over here is that if the boy plays first and then the girl follows, then you will have a different subgame perfect Nash equilibrium that will be cricket cricket. You can just verify, and it is not very difficult. You have to just uh, interchange the positions of boy and girl, and then you will have to find using backward induction what is the subgame perfect Nash equilibrium, and it will come out to be cricket cricket for that case. Now for this case we have movie. Now what are we interested over here? We are interested to see what is a non-credible threat. So you see, when the girl is playing movie, the boy is getting a utility of 1 if he plays movie and a utility of 0 if he plays cricket. Now, can the boy say, if you are playing movie, I will play cricket? That is, instead of you getting a utility of 2, I will make your utility 0. Can this threat be given by the boy to girl? What he will say, that if you are playing movie, I will play cricket. He cannot do that because his utility from 1 will become 0. You see, why will boy say this threat? You see, if the girl plays cricket and he plays cricket, he will get a utility of 2. Instead of that, he is getting a utility of 1. So he wants to maximize his utility. So this threat he wants to give to the girl, that if you play movie, I will play cricket and sabotage your utility. But he cannot do that because the girl knows he will not play cricket. Why? Because his utility is also decreasing from 1 to 0. Suppose his utility over here was not 0 and it was 1. Suppose his utility over in this case, when the girl is playing movie and the boy is playing cricket, was 1, the utility of the boy, then this threat would have been credible. The boy would say that I will play cricket, not movie, if you play movie. Then his utility for cricket is also 1 and his utility for movie is also 1. Therefore, this threat would have been credible. Alright. So this is what a non-credible threat is. When his utility over here is 0 and he is saying I will not play movie, I will threaten you by playing cricket, this is not credible because the girl knows that his utility is more if he plays movie instead of what he will get when he play cricket. Therefore, he will always play movie when the girl plays movie. Right? So this is what the idea of non-credible threat is. If you have any doubt, you can just uh, stop me, or I will just reiterate it again because, uh, yeah, should I? Okay, so I'll just briefly tell this again. So you see over here, what is the Nash equilibrium, subgame perfect Nash equilibrium? It is coming out to be M comma M. All right, how it is coming? The boy from this subgame, he is playing movie, and from this subgame, the boy is playing cricket. Now the girl will see her utility. So when she plays movie, her utility is 2. When she plays cricket, her utility is 1. Therefore, the girl will play movie. Now the boy has got a utility of 1 when playing M comma M. Now he sees that he can increase his utility when the strategies of both the players was C comma C. In that case, this would have been the utility. So the boy would say that I will play cricket if you play movie because I want to sabotage your utility. So don't play movie, play cricket. The girl will say this threat is not real. You will not do that. Why? Because if you play movie, when I play movie, your utility is 1. But if you play cricket, when I play movie, your utility is 0. Right? Your utility is 0. Therefore, you will not play movie. Sorry, therefore you will not play cricket, and your threat is not credible. All right. So this is what a non-credible threat is, the idea of non-credible threat. All right. So we'll move forward. Do you have any doubt? Aman, are you here? All right. So I'll assume that you have understood, and we will go to the next section, which is talking about Bayesian Nash equilibrium. So this is where this week's lecture begins. The first question which I have here is a conceptual question. So you can take a minute and read, and then I will read through again, and then I'll explain you the solutions. All right. So take a minute and read. Aman, are you here? Okay. So we will see what this question is about. It says that which of the elements of the game are different from a game with complete information when we are trying to find out the Bayesian Nash equilibrium of a game with incomplete information. So you see these terms, complete information and incomplete information, are new in this section. Earlier, we had talked about, or in professor has talked about, perfect information and imperfect information. So the perfect information and imperfect information came in the section where the discussion was about sequential form game, where we can have a simultaneous game inside of sequential game. All right. So if you don't remember, you can just go back and refer where we had got these two terms, perfect information and imperfect information. In short, imperfect information is when the player doesn't know what node or what action has been played prior to it. All right. And perfect information is that when he knows. So suppose in this example, in the earlier example, when the boy is here and he's thinking about it, what action to play, he knows that he is here. That is, the girl has played movie. Therefore, this is a case of perfect information. If suppose this was a simultaneous move game, so we had drawn a dotted line in between these two nodes, and therefore boy doesn't know what action has been played by the girl, and they will both play simultaneously. So that was a case of imperfect information. But now in this week, we are talking about complete information and incomplete information. All right. So if you remember clearly, incomplete information is when, so incomplete information, we say that all the players know what are the payoffs of each of the players are, what are the action of each of the players are, and who are the players. So those are common knowledge. In incomplete information, some of the features of this whatever discussion we had done for complete knowledge is missing. So the question is, which element of the game is missing, or which element of the game is different when compared to incomplete information, which has been taught in this week's lecture. All right. So this is referring to this week's lecture. Can you tell me what things is different? All right. You see, when you have incomplete information in this week's lecture, we talked about that players are not unique. All right. Players are not unique. So players have types. All right. So they can be of different types. So for example, you can think of it as a player having different personalities. A player can be of personality A, or it can be of personality B. All right. So these kind of things, or maybe twin players, twin A or twin B. So he's same player, but one can switch between those two. Right. So there are different types of players. So what do I mean by different types of players? You see, one type of player may value one set of strategies differently than the other set of players. So for example, in the previous case, when we had cricket, the boy had a utility of 2 and the girl has a utility of 1. So these utility may change depending upon the type of player uh, we have. All right. So some may have a higher utility for cricket, or the boy may have a higher utility of movie, depending upon which type of player he is. So this is the first difference between the complete information game and incomplete information. All right. We have types of players. The second is there is beliefs about. So we have beliefs which are commonly known about the belief. So there is common prior beliefs. Common prior beliefs. All right. So what does this mean? You see, the players doesn't know what is the type of the other players. So we may have different types of other players, but what are the types of other players and what distribution or what is the probability of a player being of one type is known to both the players. So suppose I am a player and the other player which I am playing with can have three different types. So I know what are the different types of the other player have, as well as what is the distribution of those probability distribution of those types. So the first type can have a probability of 1/3, second can also have a probability of 1/3, third can also have a probability of 1/3. This is an example. All right. So this is known to me, and the other player also knows that I know this information. So it is among like common knowledge. So this prior beliefs is a common knowledge. Similarly, the other player will know my types, and what is the distribution, probability distribution of those types is known to him, and I also know that he knows that what is the probability distribution of my type, and this can go on and on. All right, it can chain up to infinity. All right, just like what we did for common knowledge. So these are the two things which are different. All right, now you may ask that what about payoffs? Are payoffs not different in complete information and not incomplete information? You see, when you specify type of a player, the payoff is fixed. So there is no uncertainty in payoffs. The uncertainty is only there in the type of a player, right? So given a type, so suppose we have player 1A and player 2, sorry, player 1A and player 1B. Suppose I have given you that this is player 1A, then you are sure that what is his payoff. So there is no uncertainty in payoff. There is no uncertainty in action. The uncertainty is only there in the types of players. All right. So you don't know what the type of the other player is. That is it. The payoffs will be exactly known if you know the type of the player, or in other words, you know the payoffs of each type of the player. So if you have three types of the other player, you exactly know what is the payoff of the first type, you exactly know what is the payoff of the second type, and you exactly know what is the payoff of the third type. Therefore, the payoffs are not uncertain. Actions are also not uncertain. When you have players, there are common prior beliefs. So both have information about the type of the players, not information. They have beliefs of what the other player types are, and they have players have types, and this is unknown to the other player. What type the player is. All right. So these are the different elements in a Bayesian Nash Equilibrium game when we talk about Bayesian Nash Equilibrium, and this is what we had discussed. This professor had discussed in this week's lecture. All right. Now we will come to problems. All right. So this is the first problem. What is this problem? This problem talks about that you have player 2 which has two types, player 2 type A and player 2 type B. Right? And player 1 is only one type. So player 1 is only one type and player 2 can have two types, and your question is find the Bayesian Nash equilibrium. It is given that player 2 of type A is can happen with probability 0.5. Similarly, the other will be also having a probability of 0.5 because the sum of the probability should be 1. So player 2 can either be type A or type B. We have got the payoffs. You see, when you know exactly what a type of player is, you exactly know what the payoffs of that player are. Now you have to find out the Bayesian Nash equilibrium. So just try it out. Um, there was few examples in the class also, or in the recordings also, how to solve this problem, and then we will move on and discuss how to solve this problem. Or if you have doubt, you can just put yourself and speak, and then we'll discuss how to solve this problem. I will not do this in this slide because it becomes messy. I'll just go back and do this in a notepad. All right. So the question I'll just show you again. So this was the question. We have uh, player 1 and player 2. Sorry. We have two players, player 1 and player 2, where player 2 can have two types, type A and type B. All right. So, and the payoffs are given, and player 2 of type A can be with probability half, and player 2 can be of type B with probability half. All right. So this you have been given, and you are asked to find the Bayesian Nash equilibrium of this game. We'll see how to solve this problem. You can take 1 minute. So can you unmute yourself and speak? What should we do at this point? You see, when I say player 2 is of two types, that is, player 1 is not sure what is the type of player 2. Player 1 doesn't know what type player 2 is, but player 2 knows exactly because has been given that I am of type A or type B. So think of it like player 2 are twins. There are two players of player 2, and twin A can also come, twin B can also come. Player 1 doesn't know whether it is twin A or twin B, but player 2 knows whether I am twin A or twin B. Therefore, player 2 exactly knows what type he is, but player 1 doesn't know. So what will happen is player 2 will try to find out some kind of expected utility. Suppose player 1 comes or player 2 comes, what will be my utility if he plays this action? Something like that will happen, okay? Because player 1 is uncertain. Player 2 knows exactly what type of player he is, but player 1 is uncertain. So therefore the expectation of utility will come from player 1 and not player 2. All right. So this is the core idea of this um, solution method. Okay. Think about it. All right. Then we'll see how. I'll just mute this phone. All right. So you see, we have player 2, which is of two types, but player 1 is uncertain. What is the type of the other player? So therefore, we'll find the expected utility of player 1 given player 2 can be either of the two. All right. So how will we write this? You see, when I'm not sure what is the type of the other player, we will consider any combination of the two players. So I'll say player 2A. So I'll just say player 2A is of L. So I'm representing left as L and right as R. So I'll say player 2A is L and player 2B is R. All right. So this is player 2. So player 2 type A is L. So first will represent type A and the second will represent type B. All right. So this is how we'll represent it. Or we will say, so we have written LR, then we'll say LL. First we'll say LL because we'll just match this LL, LR, RL, RR. All right. So LL, LR, LL, LR, RL, RR. So what does this mean? It says that player 1 is of player 2 type A is of playing left and player 2 type B is also playing left. Alright. Similarly, player 2 type A is playing left and player 2 type B is playing right and so on. And for player 1, there are only two strategies, which is up and down, which is up and down. Alright. And just zoom out so that you can see this clearly. Alright. Now you see, when I'm saying player 2 has one strategy which is up and other strategy down, he can have different utilities. So when I say player 1 is playing up, player 1 is playing up. So what is the utility of player 1? Utility of player 1 when he is playing up and the other player 2 is playing left comma left. So if he is of type A, he is playing left, and if he is of type B, he is playing left. That will be the expected utility he is getting from these two. So therefore, it will be half times when he is playing up and player 2A is playing left, which is 2, and half times when he is playing up and player 2B is playing left, which is also 2. Therefore, this will become 2. Right? So this will be 2. Again, utility of player 1 when he is playing up and the other player is playing LR. So what does this mean? Player 2A is playing L and player 2R is playing, player 2B is playing R. So you can just write it half. So this is equals to half times. You see, he's playing up and the other player is playing left, which is 2, plus half times he is playing up but the other player is playing R, which is 0. All right. So this will be 1. Alright, so we'll write this 1. Similarly, utility of player 1 when he is playing up and the other player is playing RL, will be half times. You see, he is playing up in the first game, he is playing up, and player 2 is of type A, which is playing R. Therefore, his utility is 0. Alright, so he will get 0. And half of the time when he is playing up and the other player is playing left, then he is getting a utility of 2. Therefore, he will get a utility of 1. Okay. Similarly, utility of the first player when he is playing up and the other player is playing R comma R. What does this mean? Player 2 of type A is playing R and player 2 of type B is playing R. So half. So where is this half coming from? This probability is 0.5. So I'm writing it half. So half of the time he is getting a utility of 0. Why? Because he is playing up and player 2 type A is playing right, which is 0. And half of the time he is playing up and the other player is playing 0, which is also playing right, which is also 0. Therefore, he will get a utility of 0. Right? And we'll do this again when the strategy of player 2, sorry, not player 2, player 1, the strategy of player 1 is down and all these four cases. All right, so we'll just do this quickly. L comma L. So what is this utility? It will be half when he is playing down and player 2A is playing left. So when he is playing down and 2A is playing left, he is getting a utility of 0. All right, plus half when he is playing down and the utility and the player 2 of type B is playing L, he will get a utility of, you see, he's playing down and other player is playing 0, sorry, not 0, left, then he'll get a utility of 0. Therefore, this utility will be 0. Okay? Again, utility of player 1 when he's playing down and the other player is playing LR. So what does this mean? Player 2 of type A is playing L and player 2 of type B is playing R. So in this case, you see half times when he is playing down and other player is playing left, he is getting 0. And when he is playing down and the other player is playing right, he is getting a utility of 1. You see 1. Right? So this is 1. It will become half. Again, so I'll write this over here, half. Now again, we'll write utility of player 1 when he is playing down. The other player is playing R comma L. What does this mean? Player 2 of type A is playing R and player 2 of type B is playing left. So why I am reiterating this again and again? Because this is important. When the game becomes involved, you have to remember what we are doing. Right? So half of the time, player 1 is playing down and player 2 is playing R. Alright, player 2 is playing R. So his utility is 1. His utility is 1. And half of the time he is playing D and the other player is playing L. He is playing D and the other player is playing L. His utility is 0. Alright, therefore it will be half. So I'll write here half. Now utility of player 1 when he plays down and the other player, player 2 is playing R comma R. Again I'll repeat, player 2A is playing R and player 2B is playing R, which will become half times. You see, player 1 is playing down and player 2 is playing R, he's getting a utility of 1. Alright, so this will be 1 plus half times when he is playing down and the other player is playing R, he is getting a utility of 1 again. So therefore this will become 1. Alright, so this is the matrix. I'll just zoom a little bit. So this is the matrix. Now what will we do? We'll find the best response of player 1. Alright, so this is for player 1's utility. What is the best response of player 1? When player 2 is playing LL, you see U is the best response. Again, when player 2 is playing LR, so what does player 2 playing LR means? It means player 2 of type A is playing L, player 2 of type B is playing R. You see, player 1 is getting a utility of 1. Other hand, if he plays down, he gets a utility of half. Similarly, when player 2 is playing RL, player 1 should play up because he has a higher utility. And when player 2 is playing RR, player 1 should play D because it is a higher utility. So we have found out the best responses of player 1 for the different strategies of player 2. Now we'll do this again for player 2. So we have done this for player 1. Now we'll do this for player 2. For player 2, you see, when player 1 is playing up, so when we are talking about A, so what is happening? You see, we have find out the utility of player 1. Now what will we do? We will find out the utility of player 2. Since player 1 was uncertain, what is the type of player 2? Then we have found out a new table where the utility we have written as the expected utility player 1 is getting for different types of player 2. But player 2 exactly knows his own type because he will be given that type. I am type A or I am type B. Therefore, we don't have to find the expected utility of player 2. We will go to that table for that type and then find out his best response. So suppose player 2 is type A. So what will the table be? This will be the table. All right. Now, when this is the table, sorry, if this is the table, you see when player 1 is playing up, the best response of player 2 is to play left. When player 1 is playing down, the best response of player 2 is to play right. Is this all right? Is this all right? Again, when player 1 is playing up and player 2 B, so we are talking about player 2 of type B. The best response of player 2 is to play right. When player 1 is playing down, the best response of player 2 is to play left. Right? So when player 2 is of type A, his best response will be left if player 1 is playing up, and his best response will be right if player 1 is playing down. So what will we do? We'll find out the intersection of these utilities. Sorry, not utilities, best responses. A up for three cases: LL, LR, and RL. LL, LR, and RL. All right. Now for LL, so suppose player 1 is playing U when the other player is playing LL. So what we'll do, we will see is playing LL best response of player 2 when player 1 is playing U. So what I am saying, just uh, listen it very carefully. I am saying when player 1 is playing U, is playing LL best response of player 2. So you see when player 1 is playing up player A, so player 2A, the best response is to play L. When player 1 is playing up and player 2's best response, player 2B's best response is not to play L, is to play R. When player 1 is playing U, best response of player 2 is to play L, LR, all right, L comma R. So we have found out one Nash equilibrium, which is up comma L comma R. Right. So when player 1 is playing up, which is his best response, you see when LR is being played, U is the best response of player 1. And for the other side also, when U is being played, LR is the best response of player 2. Therefore, there is an intersection of the best responses for both the players. And therefore, this is one Nash equilibrium. We'll see if there are other Nash equilibriums also. All right. So we have seen this. This is not a Nash equilibrium. We have seen this. This is a Nash equilibrium. Now we'll see this RL. Now when player 1 is playing U, we have already seen the best response is to play LR. We will see if this is also a best response or not, RL. So you see when player 1 is playing U, the best response of player 2A is to play L and not R. Therefore, this strategy set cannot be a Nash equilibrium. All right. So what is remaining? This is remaining RR. Now when player 1 is playing D, the best response. So when player 1 plays D, the best response of player, sorry, response of player 2A. What is the best response of player 2A? You see, player 1 is playing D. The best response of player 2A is to play right. And when player 1 is playing down, the best response of player 2B is to play L. All right. So when player 1 is playing down, the best response of 2A is to play R, and the best response of 2B is to play L. Therefore, you see this RR when player 1 is playing down is not a Nash equilibrium. All right, because When player 1 is playing down, the best response of player 2A is to play R, and the best response of player 2B is to play L. Therefore, this is only the Nash equilibrium of this game, ULR. Okay, so there is only one Nash equilibrium, only one Nash equilibrium. What did we do? First, we knew that player 1 is uncertain about player 2's type. Therefore, we found out the expected utility of first player for all the strategy set for player 2. Either it can be player 2A or player 2B. We found out the best responses of player 1 for each of these strategies. Given this best response of player 1, or before that, we found out the best responses of player 2. Next, what did we do? We saw that given the best response of player 1, is each of these strategy set becoming a best response of player 2 or not? If a best response of player 1 gives a best response of player 2, which is in this set, strategy set, then that intersection becomes a Nash equilibrium. Alright, so there is only one Nash equilibrium. Player 1 will play U and player 2 will play L, R. Now, before proceeding, what is this idea? So I'll give you one example. Suppose there is a firm and the firm doesn't know that in upcoming time whether he will become type A or type B. Suppose there is some uncertainty coming in next few months and the firm doesn't know that he will become type A or he will behave in type A or type B. It is uncertain for firm 2, but that firm. But when the time comes, he will either become type A or type B. So what will that firm do? That firm will try to move in such a way that in either of the case, his expected utility is good. Therefore, this firm is actually representing player 1. Player 1 doesn't know whether he will become type A or type B, or it means whether that nature will force that firm to become type A or type B. All right. So that firm doesn't know. Therefore, he will find out some action set, some action that in both the cases he is doing good. Either if it becomes A or it becomes B, doing good. Therefore, player 1 will play in such a way that whether player 2 becomes A or becomes B doesn't matter. I will play such an action that in both the cases my expected utility in overall expected utility is maximized. Alright. So this is the whole idea of this Bayesian Nash equilibrium. And by the way, this is not just Nash equilibrium, it is Bayesian Nash equilibrium. Alright. So this is the next question. It is very similar to the previous question. We have two types of player 1. So this you have to make sure that you divide it clearly. You have player 1 which is of 2 type and player 2 is of 1 type. And we are not given probability P. Alright. So you have to find this probability P, and then for that probability you will be able to find out the Bayesian Nash equilibrium. Player 1 can be of type A or type B, and player 2 is of 1 type only. Right? And all the payoffs are given for both the players. We will do exactly the same thing. For player 2, we will have to find out the expected utility he is getting. And then we will see what is the Bayesian Nash equilibrium. Right? Before that, this game is slightly interesting. You try and then we'll show you what is different from the previous game. Right? Just try. I'll give you 1 minute. I'll not remove the microphone or the speakers. Otherwise, I'll not be able to hear you. All right. So are you trying to do it or solve it? I'll give you one more minute. Just try. Okay. So are you here, Aman? All right. So you see, we have two types of player one. All right. So you see, when we have two types of player one, then player two is uncertain about what is the type of player one, but player one knows. So suppose we are in this game, therefore player one knows he is of type A. Okay? Player one knows that he is of type A. Now when player one knows he is of type A, then he can find his best response. So we'll just see what is the best response. So when player two is playing left, the best response of player one is to play down. I'm correct? Am I correct? You see, when player 2 is playing left, when player 1A plays up, he gets a utility of 3. When he plays down, he gets a utility of 4. Therefore, 4 is more than 3 and he will play down. His best response is to play down. Similarly, when player 2 plays right, the best response of player 1A is to play down. Therefore, you see, this strategy or this action down is the dominant strategy for player 1A. Therefore, player 1A will never play up. Player 1A will never play up. Sorry. We'll do this for player 1B as well. Alright. You see, when player 1 knows he is of type B, he can find out his best response. So when player 2 plays left, his best response is to play up. And when player 2 plays right, his best response is to play up. Therefore, down is a strictly dominant or strictly dominated strategy. He will never play down. He will only play up. Right? Now, you see, there is only we have reduced the game. We have reduced the game. Now you may think that for the first game where player 1 is of type A, we can further reduce this game. How? Because you see, player 2 will think that if he plays left, because player 1A will never play up, it is just taken out from the game. So player 2 will think if he plays left, he will get a utility of 3, and if he plays right, he will get a utility of 0. So you might be tempted to remove this strategy right altogether. So you might be tempted to remove this strategy right altogether. If you go to the second game, you see, suppose player 1 is of type B, player 2 will see that left is getting dominated by right. Therefore, you're saying to remove the strategy left. So overall, what are you saying? For type A, you remove right, and for type B, you remove left. So you cannot do that. You see, player 2 is uncertain about the type of player A. They're playing simultaneously. So he doesn't know player 1 is of type A or type B. Therefore, you cannot remove this. So this dominated strategy which we had removed, like eliminated sequential elimination of iterated elimination of dominated strategy, you cannot do this for player 2. All right, so is this clear why we cannot do this player 2? Because player 2 doesn't know if he is in game type A or game type B. But you could do this for player 1. Why? Because player 1 exactly knows if this game is of type A or type B. Therefore, you could do this for player 1. Now, only one action is for player 1A and one strategy is for player 2. So you can just ignore other strategies. So when you are trying to find out the utility for player 1, for player 2, how did we do? Previous case, we found the expected utility. We will do this again. So player 2 has two strategies, left and right. Left and right. Now, player 1 will either play player 1A will play down because there is no other strategy, and player 1B will play up. So there is only one combination, down and up. There are no other combination. for player 2. Player 2A will play down and player 1A will play down and player 1B will play up. There is no other combination to consider for player 2. Alright, so we'll find out the expected utility of player 1 given he plays L and the other player plays D U. That is player 1A plays D and player 1B plays U. So what is the expected utility? You see, what is the probability player 1 will be of type A, which is P. So we'll write P times the utility of player 2 will be 3 when he plays left. Alright, so it will be 3 plus, so you see if this is having a probability of P, this will have a probability of 1 minus P plus 1 minus P times player 1 B is playing U and player 2 is playing left, so he's get a utility of 2. Alright, so we'll just solve this. So when we solve this, what we see is this will become 3P plus 2 minus 2P, which is actually 2 plus P. 2 plus P. Again, the expected utility of player 1 when he plays R, I'll write this 2 plus P. When the expected utility when he plays R and the other player is playing DU, what will this be? You see, with probability P, he will get a utility of 0. He will get a utility of 0. And with probability 1 minus P, he will get a utility of 4. With probability 1 minus P, he will get a utility of 4. So this utility will become 4 minus 4P. So this is 4 minus 4P. So we have found out the best response of player 1 and also, so this is the best response of player 1, DU. Player 1A will play D and player 1B will play U. Now we have to find out the best response of player 2. So if 2 plus P is greater than 4 minus 4P, then the best response of player 1 is L. Right, so we'll solve this and find out the this P. So what will this P be? 5P greater than equals to 2 or P is greater than equals to 2. So when P is greater than 2 by 5, this Bayesian Nash equilibrium is what? Is L comma DU. Therefore, this is the Bayesian Nash equilibrium and L is the best response of player 1. If P is less than 2 by 5, then Bayesian Nash equilibrium. So when P is less than 2 by 5, the best response of player 2 will be R, alright? Because this utility will be more than this. So this will be R comma DU. And when P is exactly equal to 2 by 5, then both are Bayesian Nash equilibrium, right? So both this and this will become Bayesian Nash equilibrium. So it depends upon the probability P. When you fix this probability P, you will get the exact Nash equilibrium. Alright. Since we don't know the value of P, therefore the Bayesian Nash equilibrium depends upon the probability P. Any doubt? Just think over it. I'll give you few minutes and we are taking a break. We will come back at 7. Alright. It is currently 6:54. We'll come back at 7. You take a minute and think about it. If you have doubt, after the break, we can discuss. Okay? Hello. I have kept this slide over here. You think about it and we'll meet at 7 exactly. So I'm sorry, the screen got turned off. I'll just share the screen again.
Share the screen.
Okay, so we'll just wait for 2 minutes and then we'll go to the next slide. So if you have any doubts, you can just ask me now, or if you're not here, then we can just begin at 7. That. No, no. Shall we start? All right, so we are starting. So you see, this is a very similar game, but over here we are exactly given the probability. What is the probability? One player is of type. So you see, we have over here player T2 is of two types, type A or type B, and the action sets are similar: left, right, up, down. Right? So in the previous case, we had some simplicity. The problem was a little bit simplified because there were dominant strategy. In this example, you will see that that is not the case, and therefore this is a little bit different. All right. So now you make this note that we have two types of player 2. Right? We have two types of player 2. Now when we have two types of player 2, player 1 is uncertain of what is the type of player 2. Therefore, we'll find out the expected utility of player 1 and not player 2. Okay? So we'll have to find out the expected utility of player 1. Player 1 has action set up and down. Alright. Now let us first find out the best responses of player 2, because player 2 will exactly know if he is of type A or type B. When player 2 is of type A, the best response of player 2A when player 1 plays up is to play right. Alright. And when player 1 plays down, the best response of player 2A is to play right. Therefore, you see, player 2A has a dominant strategy, which is right. Therefore, you can just remove left altogether. Similarly, in the other game, when player 2 is of type B and when player 1 plays up, the best response is to play left. On the other hand, when player 1 plays down, the best response of player 2B is to play right. In this game, you see there is no dominant strategy. Therefore, you will have combinations of strategies for player 2 when you consider the utility of player 1. So you see, player 2A will always play right. Alright, will always play right. So you will have either right left or right right. Right. So this is for player 2. Either player 2 will play right left, that is player 2A is playing right and player 2B is playing left, or right right. Now we'll have to find out the expected utility. Therefore, utility of player 1 when he is playing up and the other player is playing right left, which will become, so you see the probability is given, which is 0.2. So it will be 0.2 times. What is the utility? So you see, when he is in type A, sorry, so the utility is actually 0. Right? So it will be 0 plus when he is of, when the player 2 is of type B, when he plays up, his utility is 3, because player 2B is playing left. Player 2B is playing left, so it will be 0.8 times 3. Is this all right? So it will become 2.4. It will become 2.4. Expected utility of player 1 when he plays up and the other player is playing RR. So we'll just find out. It will be 0.2 times. You see, first player is playing first player is playing up and the second player of type A is playing R, which will become 0 plus 0.8 times. First player is playing up and the second player of type B is playing right. His utility is 0. Then this will become 0. Alright. Again, utility of player 1 when he plays down and the other player is playing RL. This will become 0.2 times. You see, he is playing down and the other player is playing right is 1. So this is 1 plus 0.8 times. Why 0.8? Because the probability that player 2 is of type B is 0.8. 0.8 times player 2B is playing left. Player 2B is playing left and player 1 is playing down. Then the utility he is getting is 2. Then it will become 1.6. Right? So it will be 1.6. 0.8 times 2. No, 0.8 times 2 plus 0.2, which will be 1.8. So this is not 1.6, it is 1.8. Utility of player 1 when he plays down and the other player is playing RR. So it will be 0.2 times. He is playing down and 2A is playing R. So his utility will be 1 plus 0.8 times. He is playing D and the other player is playing R, which is again 1. So this will become 1. Alright. Now we'll have to find out the best response of player 1. So you see, when player 2 is playing RL, the best response of player 1 is to play U. And when player 2 is playing RR, the best response of player 1 is to play R. Therefore, we have found out the best response of player 1. Now we'll see if, so we'll find out the Nash equilibrium. Alright. So you see, when player 1 is playing U, the best response of player 2A is to play R. Alright. So we have written that for both the cases. Now we'll just have to see for player 2B. So when player 1 is playing U, the best response of player 1 is to play L. Therefore, this is the intersection of best response of player 1, player 2A and player 2B. So therefore, U comma R comma L is a Bayesian Nash equilibrium. Again, when player 1 is playing D, player 2A will play R. We have clarified this. Whether he will play R when he is 2B or not, we'll have to see. When he is playing D, when player 1 is playing D, player 2B will play R. Therefore, D comma R is, so this is D. So just write it clearly. D comma R is a Bayesian Nash equilibrium. So therefore, this game has two Bayesian Nash equilibrium. You see, you have to think that each of the types are also a player. Something like that. Each of the type is also a player, and you have to find out the best response of each type. So when you find out the best response of each type of players, and then you find out the intersection of those best responses, then you will get a Bayesian Nash equilibrium. So these two strategies are when the best responses intersect, and these best responses are for each player and their each type. Therefore, we have found out the Bayesian Nash equilibrium for this game. You just check this out again. I'll just keep this slide here for 1 minute. If you have doubt, then just ask again. Then we'll move to the next problem. So there are two Bayesian Nash equilibrium for this game. Aman, do you have any doubt? All right, so we'll move to the next problem. So this is a similar problem than the previous one. Just the way we have expressed the utility of each player is different. That is it. All right. So player one knows the value of C. Why? Because player one is of two type. Right. So the question you have to, from the question you have to know whether player one is of many types or player two is of different types. All right. So player one has two types. You see, C can either take value 0 or can take value 3. So two types. All right. So where C can be 0 or 3. Right? So you can write it like this. C belongs to the set 0, comma 3. You can either take value 0 or it can take value 3. So when it takes value 0, this utilities will change accordingly, and it takes value 3. So we'll write those utilities separately, and we'll solve this similar in a similar way that we have solved the previous examples. So player 1 is of two type and player 2 is of one type, but he believes that player 1 takes value 0, not player 1, sorry, C takes value 0 with probability 1/4 and C takes value 3 with probability 3/4. So therefore, player 1 of type A will be 1/4 of the time and player 1 of type B will be there for 3/4 of the time. So let us just draw the um, this is called, I'm sorry, game table. All right. So for C is equals to 0 we will draw, and for C is equals to 3 we will draw. Right. So this is an entrant game. So we had seen this game. So he can either enter or remain out, and the incumbent can either fight or accommodate. All right. So I'll just write it over here again. So when C is equals to 0, F1 firm 1 is of type A, and when C is equals to 3, firm 1 is of type B. Right? Firm 1 is of type B. I'll just write it like this. He can either fight or accommodate, and firm 2, so firm 2 can either enter or remain out. Firm 1B can also fight or accommodate, and firm 2 can either enter or remain out. Right? When C is equals to 0, the utility will be 3 comma minus 1, 5 comma 0, 2 comma 1, and 3 comma 0. Right? So this is the table for C is equals to 0. When C is equals to 3, you can just find out the utilities is 0 comma minus 1, 2 comma 0, 2 comma 1, and 3 comma 0. Just check again if I have not made any mistake. If you think I have made a mistake, please point it out. All right. Let's check. Now I would like you to do this problem. You see, it is a very similar problem. We did two questions previous to this. Very, very similar problem. Just check and see why I'm saying that. Before that, this can happen 1/4 of the time and this can happen 3/4 of the time. Right? So these are few important details. Now you remember the idea. Player 2 is uncertain about the type of player 1. Alright. So the expected utility which we calculate, which will be of player 2 and not player 1. And by the way, if you're thinking why have I only taken the cases where one player has two or three types and the other player is only of type 1, it is just for simplicity. We can have multiple types of both the players, and I have taken one example where player 1 is of two type and player 2 is also of two type, and we'll see how to solve that problem eventually. All right. So just solve this problem first and then we'll move forward. All right. Try, at least try, and then we'll see how to solve this if you're not able to solve it. All right. We will see how this happens. So you see, in this game, we will solve it first. We will see the table first when player 1 is of type A. You see, when player 1 is of type A, player 1 exactly knows what is his payoff. Therefore, we can find out if there is any. So we can find out the best responses for that player. So when player 2 is playing E, the best response of player 1A is to play F. Any doubt? Similarly, when player 2 is playing O, the best response of player 1A is to play F. So you see that playing A is a strictly dominated strategy. He will always play F. Player 1A will always play F. Similarly, when player 1 is of type B, we will find out the best response of player 1. When player 2 is playing E, his best response is to accommodate. And when player 2 is playing O, his best response is to accommodate. Therefore, he will not fight. He will always accommodate. So what is this example, by the way? You see, this is an example where firm 1 is of two types. Either he can be a strong firm or he can be a weak firm. When he is a strong firm, he is better off fighting. He is better off fighting the entrant. When he is a weak firm, he is better off accommodating the entrant. Alright, so this is how this game is. When he is strong, he is better off fighting that firm, and when he is weak, he is better off accommodating with that firm. Now you exactly know the best responses of the player, and you have found out strictly dominant strategies for both the type of player. So for player 2, it becomes simple. You see, for player 2, when you are trying to find out the expected utility, if he should enter or remain out, the strategy set of player 1 is only one combination. What is that? It is FA, when type A fights and type B accommodates. Okay, this is for F1, A and B. Type A fights and type B accommodates. Now we'll just quickly find out the expected utilities. You see, expected utility of player 2 when he is playing accommodate and the other player is playing FA. So this probability is 1/4. You see, it is 1/4 of the time. When he's playing E, he's getting a utility of -1. And when he's playing E in this game and the other player is playing A, he's getting a utility of 1 plus 3/4 of the time he's getting 1. Right? So you see, just check again. 1/4 of the time when he is playing E and the FA is playing F, he is getting a utility of -1. And when he is playing E and 1B is playing A, he is getting a utility of 1. Alright, so this will be 2/4, which is half. Therefore, this is half. U2 out and the other player is playing FA, then 1/4 of the time he will get, so he is playing out and the other player is playing F, he will get 0 plus 3/4 of the time he will get, what will he get? He will play out and the other player is playing accommodate, he will get 0. Therefore, he will get 0. Alright, so this is 0 and this is O. Now we can find out the best response of firm 2. So you see, when he plays E, he's getting a utility of half. When he's playing O, he's getting a utility of 0. Therefore, he will play E. And we have already found out that FA is the best response of player 1A and player 1B. Therefore, E, FA is a or is the only, because we have found out for all this combination of strategies is the only Bayesian Nash equilibrium. Right? We have found out for all the combinations and we have found out that this is only the Nash equilibrium. So we have only one Bayesian Nash equilibrium for this game. Right? So this is how this problem can be solved. Any doubt? If not, then we'll move forward. You can ask questions if you want. All right. So I'm assuming it is clear. So this is the same question. All right. Few things has changed. This C value, the C values are changed. It can be either 0.5 or 3. This probability is half and this probability is half. Right? So it can either be 1.5 or 3 with probability 0.5. Right? Same problem, we will proceed with a similar approach. So what we'll say, when C is equals to 1.5, we'll find one game table. And when C is equals to 3, we'll again draw a game table. Right? So if you need a minute, you can just tell me. I'll give you a minute to solve the problem yourself. So this is firm 1A, firm 1B, this is firm 2, and this is firm 2. Firm 1 can either fight or accommodate, firm 2 either enter or remain out. Firm 1B can also fight or accommodate, firm 2 can enter or out, remain out. So when C is 0.5, the utility will be, sorry, not 0.5, 1.5, the utility is 1.5 comma 1. This is 2.5 comma 0, this is 2 comma 1 and 3 comma 2, sorry, 3 comma 0. Again, when 3 it is, when C is 3, this is 0 comma 1, this is 2 comma 0, 2 comma 1 and 3 comma 1. All right, so we'll find out the expected utility of firm 2. Now first we'll find out the best response of player 1 when he is of type A, and then we'll find out the best response of player 1 when he's of type B. So when player 2 is playing enter, his best response is to accommodate. When player 1 is remaining out, his best response, just a minute, I've done some error. Okay. So this is not 2.5, this is 3.5. 5 minus C, which is 1.5, is 3.5. So when player 2 is playing out, his best response is to fight. All right. So there is no dominant strategy in this game. In the other game, you see, when player 2 is playing enter, his best response is to accommodate. When player, sorry, when player 2 is playing out, his best response is to accommodate. Therefore, playing fight in this game is not good. Accommodate is the dominant strategy, and playing fight is strictly dominated by playing accommodate. Therefore, there can be two combinations. The first combination can, for player 1, it can either be fight, accommodate, or accommodate, accommodate. So for player 1, it can either be fight, accommodate, or accommodate, accommodate, because in the second game, playing fight is strictly dominated by accommodate. Player 2 have two strategies. Either he can enter or remain out. Now what we'll do, we'll find out the utilities of player 2. Alright, so we'll just quickly do it. Utility of player 2 when he enters and the other player is fight for type A and accommodate for type B. Now the probability is given to be 0.5. So this is happening half of the time and this is happening half of the time. Therefore, it will be half times. You see, you have to be careful over here. All right. So you see, player 1, player 2 is entering and player 1A is fighting. So the utility of player 2 is 1. All right. And when player 2 is entering and player 1 is actually accommodating in this game, his utility is 1. So therefore it is 1. All right. So this will be 1. U2OFA, that is player 2 is remaining out and player 1 is A is fighting and B is accommodating, then expected utility will be half times. You see, when he is remaining out and player 1 is fighting, then his utility is 0 plus half times when he is um, remaining out and this player is accommodating, his utility is 1, so it is half. So you see, This is half. Which is half? This is half. Again, when player 2, so let's write it over here. When player 2 is what he's doing, when he's entering and the other player is accommodating, you see half of the time his utility is, so what he is doing, he's entering and this is accommodating. Half of the time his utility is 1, and half of the time when he is entering and this is accommodating, his utility is 1. So therefore this is 1. Utility of player 2 when he is remaining out, when the other player is playing, accommodate. So it will be half of the time he is getting a utility of 0 and half of the time he is getting a utility of 1. Earlier case it was this 1. Is this clear? Okay. So we'll see what is the dominant strategy for player 2. You see, when player 1 is playing FA, his dominant strategy is to enter. Is this clear? And when player 1 is AA, his dominant strategy, his best response can either be enter or accommodate. Now we'll go back and see what is the best response of player 2. So you see, when the best response of player 1, when player 1 is entering, we have a strategy FA. What is the strategy? This will be F and this is A. So we'll see when he is entering if the best response is FA or not. So when he is entering, the best response of player 1A is to accommodate. So this is not a Nash equilibrium. So this is not a Nash equilibrium. Again, we'll see for this. So when player 2 is entering, whether player 1A will accommodate? Yes, his action is accommodate. Whether player 2A will accommodate? Yes, he will accommodate. So enter, accommodate is a Bayesian Nash equilibrium. Alright, so this is one Bayesian Nash equilibrium. We'll see this. So when player 2 is out, what is the best response of player 1A? It is not accommodate, it is actually fight. So this is not a Bayesian Nash equilibrium. Therefore, there is only one Bayesian Nash equilibrium, which is enter, accommodate. Only one Bayesian Nash equilibrium, which is enter, accommodate. All right, is this clear? All right. So I was just checking if I have done this correctly or not. Yeah, it seems I have done correctly. So if you found any error, please tell me in the next class. I think I have done it correctly. Because there are some arithmetic things, no, we can just make mistakes. So if you find any error, please point it out and we will just solve it. Now this is the last question. All right, so this is the last question. This is the case where there are, so it is not 2, it is player 1 believes that C can be this and player 2 believes D can be this. So there are two types of player 1 and two types of player 2. Both have two types. Since we are having two types for both, so there can be four combinations: type A, player 1, type B. There can be four combinations, right? So player 1A, player 1B, player 2A, and player 2B. So you can have 2 cross 2, four combinations. So for these four combinations, and there are for each player there are two strategies. So you will have multiple. Actually, there will be 2 to the power 2 number of combinations of players and 2 to the power 2 number of combinations of strategies. So there are 16 combinations you have to check to find out the Bayesian Nash equilibrium. To reduce that effort, I'm not asking the question find the Bayesian Nash equilibrium. I'm not asking the question find the Bayesian Nash equilibrium. So you have to understand what I'm saying. So you see for 2a, what are the action set? It can be left, right. Similarly for this also left, right. This it will be up, down. This it will be up, down. So there will be, for each there are two combinations of strategies, and you can have four combinations of, so it can be player 1a, player 2a, player 1a, player 2b, player 1b, player 2a, player 1b, player 2b. So there can be four combinations of players and four combinations of actions. Therefore it can be 16 combinations, and for all the 16 you have to check best responses of each, and then you have to check whether the best responses are intersecting or not, and then you will be able to find out the Bayesian Nash equilibrium. I'm not asking the question to find the Bayesian Nash equilibrium. I'm just asking verify if this is a Bayesian Nash equilibrium or not. So I have given you a strategy set, and I'm asking you whether this is a Bayesian Nash equilibrium or not. All right. So for this only you have to check whether it is a Bayesian Nash equilibrium or not. All right. So this is the question I'm asking. Just think about it. How we'll do. So what is happening? You see, player 1 is also of 2 type, player 2 is also of 2 type, and the probabilities are half, right, for both. So what will we do? We will see, you see what is the strategy set? The strategy set is actually u comma u and r comma l. So this is the strategy set. All right. So what do we have to find out? We have to find out u is the, so to verify that this is a Bayesian Nash equilibrium, we have to check if u is the best response of player 1a, u is the best response of player 1b, r is the best response of player 2b, and l is the best response of player 2b. So if you show this, then you will be able to show that this is, then you will be able to show that this is a Bayesian Nash equilibrium. When you show these four, then only you will be able to show that this strategy set is a Bayesian Nash equilibrium. All right. So that is the question. For this question, you have to show that these four are actually best strategies. Sorry, best response for each of the type of the players. So I'll give you a minute. Just think about it, and then we'll begin. I have given you a quite a lot of hint. So this was a important thing to consider. When you consider this, then only you can move forward. All right. So we'll see how to solve this problem. I'll give you 1 minute. So tell me if you have thought about how to solve this problem. If you have any idea of how to solve this problem. You see, these utilities will change depending upon what player 1 type is and what player 2 type is. So for all these cases you have to solve, and then you will be able to verify that this is the best response of that particular player. All right. So I'll write few things for your understanding. All right. So when, so you see there are these unknowns C and D. So when okay, just before that, You see, when player 1A, what do I mean by player 1A? Player 1A means C is 0, right? C is equals to 0. Player 1B, what does it mean? C is equals to 2, right? For this, C is equals to 2. Player 2A, it means D is equals to 1. This is D equals to 1. And player 2B is actually D is equals to 3. So this is D is equals to 3. Correct? So for each of these combinations C and D, you can have 4 tables. So for C comma D, for each combination you can have 4 tables. And if you have to find out the Nash equilibrium for overall game, it will be difficult. To not do that, the question has been simplified to check if this is a Nash equilibrium. Right? So I've given you quite a lot of hint. So what will we do? If you want to speak, you can unmute yourself and tell me. Okay, I'll help you. You see, so I have written what do we need to do. I just need this table because that is important. So I'll just zoom a little bit, zoom out. You see, when D is equals to 3, when D is equals to 3, you see we have player 2B. So player 2 exactly know that I am player 2B. All right. Player 2 cannot be player 2A. When D is equals to 3, player 2 knows that I am player 2B. All right. If this idea is not clear, you can speak, ask. Therefore, when player 2 knows that I am player 2B, his utility will depend upon what type is of player 1 is. So utility of player 2 when he is playing L. So you see, we have to check if this is the best response or not. Right? So when he is playing L and player 1 is playing UU, what does this mean? Player 1A and this is for player 1B. Alright. So what will this be? This will be half, not half. Is it half? Yes. Half times. So player 1 will be half times when he is U and again half times when he is U. So you see, you have to be careful. When C is equals to 0, he is of type A. When C is equals to 2, he is of type B. So when he is of type A, when he is of type A, this C will be 0 and this D, so we have fixed. What is this D? This is 3. Alright. So you see, when player 2 is playing left, when player 2 is playing left and player 1A, 1A is playing up. So what is 1A? 1A is 0. C is 0, doesn't matter. We have to check only the utility of player 2 because we are interested in the utility of player 2. What is this? It is D, which is 3 plus half times when player 2 is playing L, player 2 is playing L and player 1B is playing U, player 1B is, so I have not written the table for all the cases. We'll use this table for all the cases. When 1B is playing U, the C is changing, D is not changing, so it will be 3. So it is 3. Right? It is 3. And just erase this and these also. Okay. Now, player 2 can have one more strategy. He can either play L or he can either play R. And we'll see if L playing L is the best response or not. Right? So player 1 is playing U comma U. So half of the time when he's playing R, and player 1 is playing U, he will get a utility of 2. Again, half of the time player 1B is playing U and player 2 is playing R, he'll get a utility of 2. So you see, playing L is giving him a higher payoff than playing R. Therefore, you can conclude, therefore, L is a best response of player A to B. Alright, so we have concluded this. Again, we'll do this for player 2A also. So when D is equals to, I'll just draw a line. When D is equals to 1, we are talking about player 2A. Now, player 2 exactly know that he is of type A. What he don't know, he doesn't know what is the type of player 1. Therefore, utility of player 2 when he is playing R. This is player 2 of type A, and player 1 is playing U comma U will be half times. You see, this half is because he doesn't know what is the type of player 1. Therefore, he is finding out his expected utility. Player 2 is playing R, player 2 is playing R, player 2 is playing R, and player 1 is playing U. So player 1A is playing U and player 1B is also playing U. So for 1A, he will get a utility of 2, and for 1B also he'll get a utility of 2. So this will come out to be 2. Alright. Again, when player 2 is playing L, this is 2A, and player 1 is playing U, half of the time he'll get a utility of D. You see, when player 2A is playing L and player 1A is playing U, he will get D, which is 1. And again, he will get D. You can just check. He will get D. So he's getting a utility of 1. So you see, player 2A's best response is to play R, because in that case his utility is more. Therefore, playing R is the best response of player P2A. Okay, we have shown this, we have shown this. Now we have to show these two cases as well. Alright, so we'll just use this side. What is the utility of player 1 before that? What are we talking about? When C is equals to when C is equals to 2. So we are talking about for player 1B. Alright, we are talking about player 1B. So when we are talking about player 1B, player 1 knows exactly that he is of type B. He doesn't know what is the type of player 2. Therefore, he will find out the expected utility. Expected utility of player 1 when he plays up, because we have to check for up only. When player 2 plays, so over here you see player 2 can have okay, so we'll use this because we are checking if it is the if these intersection of these best responses is there or not. So we'll keep R comma L. So player 2A, so this is player 2A and this is player 2B. Alright, so we are fixing this R and L and then we are checking if this is the best response or not. Alright, I'll just erase this for clarity. So what will this be? This will be half of the time. You see, erase this also. You see, he is playing up and player 2A is playing right. When player 2 is playing right, his utility is 1. And half of the time he is playing up player 2B. So this is player 2B. Player 2B is playing left. He is getting a utility of C, which is 2. He is getting a utility of C, which is 2. So this will come out to be 1 plus 0.5, 1.5. Again, player 1 utility when he is playing not U, we'll check other strategy, D. When the other player is playing RL, will be half times. You see, he is playing down D. And player 2A is playing right, his utility is actually C, which is 2. Plus half of the time he is playing down, and player 2B is playing left, his utility is -1, which will come out to be 0.5, and this is 1, so it will be 0.5. Therefore, you see, playing U when player 2 is playing RL is a best response for player 1 when C is equals to 2 or when he is of type B. We have to do this for, so we can write this. Therefore, player 1B playing, write it the other way, playing U is the best response of player 1B. Now, when C is equals to 0, we are talking about player 1A. U1, when player 1A is playing U and player 2 is playing R comma L, half of the time, so he is playing U, and player 2A is playing R, he will get a utility of 1. And half of the time player 2B is playing L, he will get a utility of C. Alright. So over here C is equals to 0. Right. Therefore this is half. U1 when player 1 is playing U and player 2 is playing R comma L, it will be half of the time he is getting a utility of. So you see player 2A is playing R and he is playing U, then his utility is 1 plus half of the time he is playing U, and his utility is, okay, I'll not have to check U, it will be D. Sorry for the confusion. This will also change. So half of the time he's playing D, and player 2A is playing, right, it is C, which is 0. Alright. And half of the time he is playing D, I'll just erase this. Half of the time he is playing D and the other player is playing L, which is a utility of -1. So this will become minus half. So you see, playing U for player 1A is also a best response. So I'll write this over here again. Playing U is a best response of player 1A. Therefore, this is also correct and this is also correct. Overall, each of the players are playing best response. When each of the players and their types are playing best response, therefore the best response are intersecting. Therefore, this is the Bayesian Nash equilibrium. Therefore, this is a Bayesian Nash equilibrium. Alright. You see, checking if this is the Bayesian Nash equilibrium is not difficult, but verifying that this is the only Nash equilibrium is difficult. I'll write this down. Checking that this is a Bayesian Nash equilibrium is not that tedious, but but checking if this is only the Bayesian Nash equilibrium is tedious. It's not difficult, it's tedious. So you can take this as a homework. Verify that U comma U comma R comma L is the only Bayesian Nash equilibrium. You can just do this and this idea of Bayesian Nash equilibrium will be clear. All right. So this will be a more involved problem to solve. All right. So this is how. So you take a minute. I'll just zoom out a little bit. Just see what we have done here over here. I'll give you 1 minute to see, and if you have questions, we can discuss this, because this idea is same as what we have done earlier. This is just one step ahead, or one step more, right? Just extending that idea. So check this once and then we will close for today. Just check this out. And by the way, if you solve that problem, you can just write it in the discussion section of the course that you have done the course, then the homework, and you can just post your um, homework there. I'll just see. There's no marking, by the way. It was automatic. All right. Just check if you have any doubt over here. Aman, is this clear? Okay, so I assume that this is clear. All right, so this is it from my side. I'll just close this again. So thank you. I'm Shubham Keshri, and I hope you learned today something. Please post your questions in the discussion section. I will try to answer those questions if you have any doubt or something. Right? Thank you for joining. You can just leave. Do you have any more doubt? Aman? Okay. So I'll just end the meeting now. Thank you.